Hello, everyone. Happy Monday. Let's see here. We are going to start a new module today. Today is our first step away from digital modulation and a step towards source coding, really. It's still how do we represent bits, but now we're going to decide how many extra bits to send to make sure the bits that we want to get through are correctly deciphered. So do you have any questions? Anyone got any issues that they want to talk about before I launch into the new note set, which was uploaded to Canvas maybe an hour or so ago?
Yeah, this is regarding enrollment in 526. Do you know if, as undergrads, we're going to be needing permission numbers?
I think so. It's likely falls under the purview of graduate standing or instructor consent.
Yeah,
But I will consent to anyone who's in this class who wants to take that class. I think it's an excellent idea. How to get you those permission numbers, I actually don't know, especially now. But I think that somehow we'll have to go through Yvonne, either you to her to me, or you to me to her. But I'll look into that. And if you want, I can send an update to the class if I get something from her.
cool.
All right. Anyone else? Okay, let's go to the new set of notes. Okay, so this is module 7, and it's called Coding and Error Control. If you haven't noticed, there's a lot of things called coding, a lot of things called modulation, and they're all going to be slightly different depending on the context. In this case, we are doing what's called error control coding or error detection coding. And the whole idea is that you're going to try to encode or translate certain information into a different version so that, in this case, we can detect errors. We had, for example, line coding, and that was changing information that were represented by discrete bits into continuous waveforms. So whenever you're talking about coding, you're talking about changing information from one format to another. You can think of that like a translation, if you like a English to Spanish translation. It's the same information, it's just represented in a different representation, I guess. So like I mentioned, we are going to be moving away from what we have been doing, which is channel coding or channel encoding. And now we're going to start talking about source coding. So the idea is that before we deliver the bits to the channel encoder, we're going to manipulate them. We're going to add some in, we're going to change them around, we're going to maybe change their order. But the idea is at the end of the day, we still need to have some bits ready to deliver to the channel encoder for it to do its thing. And on the flip side, bits are traveling that way, but then bits are also traveling this way. On the flip side, we are going to have taking the output of the channel decoder. So right so far, pretty much we've been talking about everything to the right here. But now we're all going to take that as given. Not perfect. We're not going to assume that it's perfect. We're going to assume that it's given. It has been designed. It is a whole, black box that we are going to use. And now we're going to focus on how, given information or given data here, how should we represent those as bits going forward? And so everything in the source encoder is stuff like analog to digital converters, quantization levels, quantization noise. What is your trade-off between storage ability and speed? So that's all kind of taking continuous things and mapping them into digital things. But we're going to do a kind of more specialized version of this, is assuming that there are already bits that have been generated, say, through your ADC. We're going to take those bits and we're going to decide, do we need to augment those bits with more bits? I have a tendency to use the word bits ad nauseum. and I will try and combat that because I use the word bit to mean both a binary digit, but also I have a tendency to use it to mean a thing or a piece, like a bit of information can be actually interpreted both ways. But if you're ever confused, like, did he mean a 1 or a 0, or did he mean a small quantity? Please just flag me, because I'll often do it without even noticing it. What we're going to do it's not channel coding, but it does fall under the broad umbrella of channel correction mechanisms. That is, things that we can do because the channel tends to corrupt data that passes from one side to the other. So the focus on this module is what's called forward error correction. We've talked a little bit about equalization. That was in your zero forcing and minimum mean squared error equalizer in the OFDM chapter. In addition to equalization, there's what's called adaptive equalization, which is the equalizer values, the equalizer filter changes over time based on if new information arises about the channel, or just if you can implement some sort of a time varying optimization algorithm. Because in your homework, you're designing an MMSE for a static channel. Adaptive equalization would be, say, designing an MMSE that changed as the channel changed. That's the adaptive in adaptive equalization. Adaptive modulation, and I guess we could say line coding here, is the same concept, right? If the channel is changing with time, then we need to adapt to that. One of the ways to do that would be to switch from, I don't know, 16 QAM to 4 QAM if the SNR goes too low. Okay, so that would be an adaptive modulation. So you're sensing how is my SNR doing? If it gets too low, then I'm going to get too many errors. So maybe I should switch to a lower density digital modulation scheme, right, from 16 to 4, which means my data rate takes a hit, but it also means that I'm less likely to make an error when decoding my symbols. Other topics that we really haven't talked about a whole lot are the diversity. So the diversity techniques is basically a broad term to mean the channel that you're currently using is a function of time and frequency and space. And so if you can capitalize on diversity in any of those three dimensions, then you can perhaps improve how your data gets through the channel. So multi-input, multi-output in this context means multiple input antennas, multiple output antennas, so that perhaps you can capitalize on some spatial diversity. That perhaps if the reason you are losing a bunch of data is that you're trying to transmit around a corner, well, then perhaps if you had more antennas here and more antennas here, then you might improve your odds of getting a line of sight from one of your transmit to one of your receive antennas. This, of course, exponentially increases your processing, because you have to decide how is your data, which data is going to go to which antenna, and then on the other side, which data is coming in through which antenna. But it is a way for you to capitalize on spatial diversity. And we haven't talked about this at all, basically. If you'd like to talk about this in 526, let me know. Like I said, I am, sorry, just a moment. Sorry about that, I'm back. I was saying, if you want to talk about this in 526, let me know. And the sooner I know what topics are interesting to you, the sooner I can prepare. Talked about OFDM as kind of a equalizer on steroids a little bit. The idea is that you can extend the amount of time that every piece of information stays in the channel, which means that if your channel has a finite amount of lag or a finite amount of intersymbol interference, then if the data stays in the channel for a longer amount of time, then the fraction of that time that you're getting interfered with goes down. So that's one way to think of OFDM. Again, spread spectrum is if the channel has a null at a particular frequency, then spreading your data out over lots of frequencies means that the amount of information that gets nulled, that gets lost, can be in some senses recovered from, because if you're spreading out, you're losing a little bit of your power, but then when you despread, you're not at a whole, you're not at an entire loss. So we are going to focus on what's called forward error correction. This is in contrast to feedback error correction, where there is a feedback loop between the transmitter and receiver to try and work out what bits were sent at any given time. This is going to be, if you like, an open loop type solution. So there is a little bit of terminology to get straight here. There are error detection strategies, which can tell you, if they tell you anything, they will tell you that an error occurred or not. And that is in contrast with error correction codes, which is they will tell you if an error occurred, what that error was, and if they can't tell you what the error was, then they, at the very least, should be an error detection. So by and large, error detection codes are a subset of error correction codes. Right? Error correction codes can sometimes correct for errors, but in an instance where the error was made, an error correction code should at least tell you that an error was made if it can't correct for it. If you can only implement an error detection code, or if your errors are so numerous that your error correction cannot correct and can only detect, then your best bet are these repeat requests protocols. That is, hey, I didn't get that, please send it again. And I hope you see that in order for your receiver to say, hey, I didn't get that, it has to have detected that an error occurred. So part of an ARQ situation is you need error detection at the very least. And like I said, there are situations in which the best error correction code won't be able to correct if you have a really, really noisy channel. But it might be able to detect. And so underlying every error correction code should be a retransmit request protocol at the very bottom that says, look, we can't sort through what was sent. Please send it again. But we know something's up. Please send it again. Questions so far? This is kind of all upper level, high level stuff. But I wanted to make sure that we all know why and what we're doing before we get into the nitty gritty of how. So let's talk a little bit about the probabilistic model of if an error occurs, can we detect it? And so the classic model for this is what's called a binary symmetric channel, or BSC. And it's kind of interesting that we come to it now at this point in this course, because we have spent so much of our time unpacking what goes on between transmit and receive. And what this model does is it says, you know what, at the end of the day, there are bits coming into the system, there are bits leaving the system. Some of those bits are going to correctly be transmitted. Some of them are going to be incorrectly transmitted. The probability that a bit is flipped shouldn't depend on the bit itself. So that's where the symmetric part of binary symmetric channel comes from, is the probability of a bit flip, so 0 flips to 1, with probability PB, is the same as the probability that a 1 flips to 0. So the probability of those events in a binary symmetric channel are the same, and I'm going to call them PB. And then, of course, the probability that a bit does not flip is the complement of that, or 1 minus PB. And as you've seen in the waterfall plots that we've seen so far, the probability of any bit getting flipped is actually quite low, right? These waterfall plots are all on log scales, and so there is usually a really good um, analytical background for why you'd assume that the PB is much, much less than a half, because otherwise it's just a coin flip, right? Um, and we're doing all our things um, like line coding, like channel coding, to ensure that the bits themselves should not get flipped. But we can't prevent them from getting flipped. So the idea is now, what if we inject some check bits so we can figure out which bits were flipped and how to flip them back? And so, yeah, basically what we've been doing is looking at the probability of a single bit error. So this is like the first half of the course, where we're doing all these waterfall plots, and on the vertical is PB, and on the horizontal was SNR. And so what I'm saying is, if you're going to consider that fixed, it means that you have considered everything downstream from your source coder as fixed. The channel is fixed, the SNR is fixed, the Voronoi detection regions are all fixed. So the idea is that we are living on some line and some curve, and so we're going to be starting all our analysis assuming that a PB is fixed. Okay. Given that probability of single bit error, then comes the question of what can we do to, or what is a good and rational and efficient method of injecting check bits in to make sure that we, at the end of the day, from start to stop, get the fewest number of flipped bits or lost bits, if you like. So there are a number of questions that follow up from that, and that is, if an error occurs, what's the probability that it's actually detected? So this is kind of akin to the idea, if something goes wrong, what's the probability that I can actually sense that something went wrong? And then we can get into kind of the second level analysis, is false negatives and false positives. That is, if an error occurs, does my scheme miss that occurs? So the scheme would say no error occurred, but that's a false statement, so we call that a false negative. And then the complement of that, or the converse of that, would be no error occurs, but the scheme tells us that an error occurred. So that would be, hey, yes, an error occurred, so that's a positive, but it's a false positive because no error actually occurred. So these three questions, and this one will be the biggest. These will kind of be secondary. There'll be kind of like, oh, given this error correction scheme, what is the resulting false negative rate or false positive rate? But for the most part, we're going to focus on designing good error correction schemes that give us a good answer to this first question. So, I mean, I think the most basic error correction scheme, I guess, should we flip here? Yeah, why don't we do this? So in this context, the transmitter is going to be calculating some code or check bits from the data bits. And so actually I'm going to ask your forgiveness, but I'm going to flip back and forth between the next slide and this slide. Okay, so this is the idea that we have k amount of data bits, and then the transmitter is gonna perform some function on those bits and generate what's called a frame check sequence. So this is known as the frame check sequence, or check bits for short. And then if we append those, they're shown here as kind of a chunk on the end. They don't have to form a chunk. They can be interspersed, kind of sprinkled amongst the data, as you'll see in a bit. But at the end of the day, we're changing k bits carrying actual data, and we're transforming that into n bits, n strictly bigger than k. of inflated bits, some of those bits are going to be check bits. At the receive end, the receiver and the transmitter both have to agree on the error correction code or the error correction scheme that's being implemented. And so in this visual representation, that means just slicing off the last n minus k bits and then running the same function on the data bits on the receiver and then making this comparison. If that comparison passes, right, if the received check bits match the computed check bits, then we have to conclude that no error occurred. But I hope you can see now that this could lead to false negatives, right? So if for some reason the same bits get flipped in here as get flipped in here that lead to a correct pass or an agreement in here, then this could lead to a false negative. No error occurred, and while in reality, just the right number of errors occurred to give us a false sense of security. Okay, so this is the root of where you can get this idea of false negatives, is that if just the right sequence of errors or just the right sequence of bits get flipped, you can land yourself in a situation where the mathematics tell you no error occurred and yet errors occurred. And I want you to see that there's no way to get around that. We can make the probability that just those errors happening is low. But the idea is that if what we're going to call code word gets translated into another code word, then you have to say that no error occurred. So here's a little bit of vocab. Is the original k bits are generally referred to as the data word. This is not like an English word, it's just a sequence of bits that we call a data word. The entirety of this, that is the data plus the check bits, is known as the code word. And so in all of these lectures, the code word will be of length n, the data word will be of length k, and then the difference, n minus k, is the amount of extra bits you're sending to try and guarantee that the bits that you want to get through correctly. Okay, so again, there's this tension between, do I send more check bits to try and ensure that fewer errors occur, or that if the errors occur, that they can be corrected for, but at the cost of more bits being sent through the pipe. And so the end data rate, the effective data rate, will go down if you send more check bits than you need. Okay, so I hope that tension is clear. And then so if you fail this comparison, then in an error detection sequence or system, this would trigger a retransmit request. In a error correction system, this would then enter into the error correction stage. Hey, then an error occurred. Let's do something about it. That's the idea. Andrew, question?
Yes. So when we put our n minus k bits for our detected, our detection bits into the thing, so it does matter if it is in like position of the data, or does it? I mean, it may matter maybe in the error correction statement, but would it matter? I guess it would, but it would also matter, depending on the false negative probability that you get. Is that so? Spreading out those bits, does that affect its probability of missing or something like, I guess. And
okay.
you have the same error sequence that comes in. If you put them over, a different spread or something like that, then you have a better chance of trying to detect that? Does the position of the n minus k bits do matter? That's, I guess, what I'm asking.
Yeah. In a binary symmetric channel, no.
Okay.
Right, because the heart of a binary symmetric channel says, I don't care what the bit was or when it occurred, the probability of any bit getting flipped is the same.
Okay.
That's a simplistic view of the world, and in fact, in a practical communication system, most of the times that bits get flipped, they get flipped in chunks of time that are dense. Right, so
Okay.
you'll have these events. Sorry, you'll have these events in time. Someone turns on a microwave, or you drive behind a big rig or a giant wall, and in time you get a null in the channel, and so the detector. Sorry, my dog is stuck under the bed. I need to take a time out.
Okay. That makes sense.
Okay.
I thought there might be an assumption of, if it's long enough, then it doesn't really matter as much. Anyway, I'll let you.
Be right back. Okay, good news. She extricated herself as soon as I took the headset off. I'm sorry. You were saying.
But I think that makes sense. It's like you can assume, an error will be long enough, no matter what the data is, and what you were saying by false negative, it had to be very perfect between those things, and not perfect, but
perfectly bad.
Yeah.
So it is true that false negatives and false positives have to happen at a lower rate than errors themselves, because in any error correction scheme that you use, you'd have to have more than one error, more than one bit get flipped in order for a false positive or a false negative to occur. And so what we're going to mostly do is we're going to mostly design error correction schemes that will correct for one bit flip out of 7 or something like that, but that they will fail in that they will give a false positive or false negative if there are 2 bits that get flipped out of 7.
Okay.
Or more. There are, and so this is a good opportunity to talk about what the alternatives are in terms of check bit placement. So if you've got, say, let's let k be, no, let's set k be 4. We'll start small. And let's let n be 7. So we're going to send 7 bits for every 4 that we actually want to send. So that's how to translate this. So what do we need here? We need his 7 bins. So 1, 2, 3, 4, 5, 6, 7. Good. And then forget I drew that. So what the cartoon here on the slide suggests is that we're going to send data bit 1, data bit 2, data bit 3, data bit 4, and then check bit 1, check bit 2, check bit 3. And in principle, and I think also mathematically, that is fine. But it does leave yourself open to what are called burst error events, which I was describing before. But another reason why you would want to not do that is, and we'll see this is kind of the beauty of what are called Hamming codes, is if you put your check bits inside your data bits, or kind of interspersed, I think you go D1 and then, no, sorry. So position 1, position 2, position 4, and then the data. One of the advantages of doing this, of sprinkling your check bits in amongst your data bits, is that the location of the check bits now carries information with it as well. Before, it was just, oh, the stuff on the end, chop it off, okay. Now, you can encode oh, this is in position 0, or sorry, 2 to the 0, position 2 to the 0. This is in position 2 to the 1. This is in position 2 to the 2. And so what Hamming codes in particular use, and then everything that was subsequent to Hamming, what they use is, in practice, the location of the check bits themselves carries information. So that's why that you would do this. But like when you're just learning about it, it makes sense. To, oh, you've got data, then you're going to glue onto the end some check bits, and that's fine. But there is an advantage to be had by placing the check bits intelligently. And then of course, like on the receive end, there's nothing stopping you from just like popping the check bits out and then saying, okay, here's my check sequence. Right. So it's a very fine line between the cartoon that's drawn on the slide and my intersprinkling of the check bits. You can change one to the other and back again, provided you know where the check bits were placed within a frame. That's the other important thing here, is that everything here is frame based. So this code word constitutes one frame. We'll also end up calling that a block as well. There are error correction and detection schemes that aren't frame or block based. They're called convolutional encoders, and we'll talk about those as well. But for starters, I think it's best to think about everything happening both in discrete time, because we've got discrete data, but also in like macro discrete time, one frame at a time. And once you translate the frame, then you can move on to the next frame. So, right, there's a lot that goes on here, and we're going to start small, and we're going to build up the complexity from there.
Okay, thank you.
Mm-hmm. Okay, so the most basic form of error detection is just appending a parity check bit. So the idea is it like, and these two are completely equivalent, and I think I'm mostly going to focus on even parity. And so what you do is you take, in this case, k equals 7, and you count the number of ones in those 7 bits. And if the number of ones is odd, then your check bit is going to be 1. So here, k equals 7. And if we're doing an even parity scheme, then the data word gets translated into a code word that is the first 7 bits, and then the check bit. And the reason that I know the check bit is 0 is because there are already an even number of ones in the first 7 bits. So at the receiver would operate in chunks of 8 bits, right? It would say 1 byte at a time, and then the last bit that comes through the channel, it compares that to the parity of the first 7 bits that came through the channel. If that parity matches, then our receiver in this context would say, no error occurred, go on your merry way. If the parity didn't match, right? If instead, so let's say, for example, at the receive side, let's say we receive 1 1 0 0 0 0 1 0. Okay, so the receiver then carves off this and says, okay, this was the check bit, and then the receiver would count the number of ones, and in this case it is 3, which means that the check bit should be 1, but the check bit was 0, so this would be an error detected. Okay, and in this case, it would be a true error. So this would be a true positive, right? Because we are omniscient in this case, and we can see that this bit flipped between transmit and receive. Can we correct? That's my question to you. Given this scheme, is this an error detection or an error correction scheme?
Correction, because there's only one. We can change. Well, it's detection, isn't it? There.
So yeah, does this operation that I've just shown us, does it tell us which bit was an error?
No.
No.
Good, it does not. So this is an error detection only. So this is an error detection. Not correction. Precisely because I had to come in and draw a big red arrow to show us where the error occurred. Nothing about this mismatch told us which bit got flipped. Yeah.
I have a question about what if there were 2 bits flipped?
What if there were 2 bits flipped? What if we have example number 2 at the receive side, and we get a 1, 1, 0, 0, 0, 0, 1, 1. Okay, what happens now? The receiver carves off the check bit. The receiver computes the check bit from here. So this is odd, which means the check bit should be 1 to bring the parity to even. And then this and this pass. Pass meaning the receiver says no error occurred. Yeah, so here this is the beguiling part of all this. Is this we've just cooked up is what, a false positive or a false negative?
False negative.
Good. False negative. So the parity check scheme that's on this slide, where you take 7 bits in and append 1 check bit, can detect 1 error out of 8, but it fails to detect 2 errors in 8. Bonus question: what does it do if there were 3 errors in 8?
It would detect that, right?
It would detect it. It would be a true positive detection. So we're starting to see a pattern, and never mind the high unlikelihood that you get, 7 out of 8 bits getting flipped. Just put all that practicality beside for a moment and see that this will either give us a true positive or a false negative, depending on the parity, actually, of bits that get flipped within each byte. Okay. I'll pause here because this is a fundamental concept, and I want to make sure everyone's on the same page.
Well, could it detect a 2-bit if a 1 and a 0 were flipped? I don't know. Oh, I guess, does that matter? That doesn't really matter, does it? It only.
Yeah, it does not matter.
Okay.
Yeah. So it does
not matter yet. The location does not matter.
Yeah. The reason that I chose to flip these 2 is because we'd already done this one, but I also wanted to show you that if the check bit's flipped, it's not special, right? It also produces a bad outcome. Yeah. So unless you do something more intelligent than just slapping it on the end, and when I say that, I mean we're going to learn about something more intelligent called Hamming codes that will allow you to say, oh, 1 bit got flipped. That bit is a check bit. Therefore, the received data bits are good to go. So Hamming will do that for us. And I'm sorry that I keep alluding to this thing that we haven't talked about, but it's coming. Let's see here. Okay, yeah. So this is a more formal treatment of what we were just talking about. So And I think this is for, this is for the same scheme that we just did. So we're going to do, this is the code word. So this would be x1, x2, x3, x4. And so this is actually, regardless of your error detection or correction scheme, this is just a way to measure error in strings of bits. So let's say we send the top row, we receive the middle row, and I've highlighted which ones got flipped for you. Then the error vector would be the, well, is it the difference of x and y?
It's like the XOR.
Yeah, that's what's
There you go. Yeah, it's not x minus y, it's not y minus x, it's actually x XOR y. So we will sometimes write that as a plus with a circle around it. Okay, so when you see me write that symbol, plus with a circle around it, that means bitwise XOR. You can also think of it as mod 2 arithmetic. So if I add 1 with 1, I get 2, but I'm going to wrap that back around to 0. But if I add 0 with 0, I get 0. If I add 1 with 0 or 0 with 1, I don't ever exceed 1, so I keep that number. Okay, so then the weight of the error vector is just the number of errors that have been made. So in this case, the weight of this error vector is 2. And then, so Hamming has his fingers all over this. And so we actually call the Hamming distance between x and y to be the weight of the error vector between them. Okay, so the number of bits that had to flip to get you from x to y. Call that the Hamming distance. Okay, so now we're gonna crack into a little bit of your kind of basic probability, and that is the probability. So forgive me here. This is a difference from the rest of the quarter. Here, the operator PR just means the probability. Oh boy, probability. And I know in previous modules I just used capital P, but we're going to have, as you can see, a lot of capital P's floating around. So PR is, the operator says, the probability of the event inside of the parentheses. So the probability of the event, the weight of the error is 1. That only happens in a binary symmetric channel. So this is assuming binary symmetric channel. That only happens if n minus 1 bits successfully get through. So these are no error. And then 1 error. Right, so this is a little counterintuitive to some people. They say, I want to make sure that we're all in agreement that the probability in a code word that is of length more than 1, that to work out the correct probability of the weight of the error vector in those two code words to be 1 is we need n minus 1 non-flips, and we need exactly one flip. Okay, so that's what I have here. So then the probability that there are 2 errors within your transmit to receive code word is we need n minus 2 non-flips and 2 flips, which is a way to say, like, you can break that up and you can say, well, I'm going to multiply and divide by 1 minus PB. And if I do that, then I can recurse in here and replace that like that. Okay, so it's a way to build the probability of larger numbers of errors in a recursive format. So again, the probability that there are m bits getting flipped means m times each individual bit getting flipped, and n minus m times each bit getting not flipped. And you can always manipulate that to be this basic probability, the probability of a single error, times this fraction. Okay. So I hope you see also that if, just broad strokes, if PB is a small number, 1%, 0.1%, then this gets small, real quick. That's not even worth writing. I guess I want to point out that this last quantity is a small number over something close to 1 raised to a big power, that kind of idea. And so I hope you see that this last quantity is going to be quite small. The probability that multiple bits get flipped in a binary symmetric channel goes down, I mean, geometrically. It's the case we have here. Okay. And this is to say that we don't typically design error correction codes to successfully detect or correct, 50% of the bits getting flipped, just because that is such a low probability event in a well-designed communication system. Okay, so if you're thinking we're going to try to correct for every possible situation, no, it's going to be better worth our time to correct for the higher probability events, which is 0 or 1 or 2 bits getting flipped out of 8 or 10 or 20 bits. These are the kind of more reasonable events to design for. Is there a question in chat? Yeah, so Jack asks, is the Bernoulli assumption to allow calculation of what was sent? The Bernoulli assumption is, technically the Bernoulli says there is a probability of one event and the probability of its complement. So I think I should have written Bernoulli of 0.5. So what this means, this Bernoulli statement, is that the probability, oh boy, the probability of sending, I'm just going to say it, I can't write it here. The probability of sending a 1 or a 0 is equal. The transmitted code word is needed to do this math, to get the weight of the error, but it's not needed to do the math at the bottom of the slide. Is that what you're asking? So while I wait for him to respond, yeah, everything down here is valid regardless of the length of the code words and regardless of the number of errors in an actual particular case. What we're doing here, yeah, exactly, is in a code word of length n, what's the probability of one error, one flip occurring? And we can do that knowing only n and knowing PB. Right? With those two figures, everything on this slide can be calculated. Okay, the above example was just an illustrative example. Okay, I'm going to end there, not least of which because the dog now has a roll of paper towels that it's shredding. Okay, I got to go, people. I'll see you later.